This video is just the basics about electronic components, what they look like and what they actually do, and how they work in fact. So let's start with one of the most common, the one that I just picked up there, the resistor. So this is a 1000 ohm resistor. I can tell that from the colour bands on it, and we'll look at that later on, how the colour bands are interpreted. However, the function of a resistor, if I use the water analogy, because the water analogy is very good. If you have a pipe with water flowing through it, and part of that pipe is narrowed down to a section, then that will restrict the flow of water through that pipe. Say for instance the main water pipe came into the house, if you put a very thin pipe in line with that, even a fairly short one, then it would really restrict the flow of water coming in, because the water would want to flow through quite quickly, but it would be forced in through this narrow channel, and the resistance posed by that narrow channel would limit the water flow in the same way that a resistor does exactly the same to electricity. It limits the flow of electricity, the flow of current. And in this case, with the water analogy, the pressure of the water equals the voltage. And it's quite interesting that the Chinese sometimes refer to the voltage as pressure, and that's exactly what it is. And the flow of the water equals the current. So the higher the flow, the higher the current. Now the construction of a resistor is usually, in the case of these ones, this is a carbon film resistor. And you get metal film, carbon film, wire wound, but one of the most common is just carbon film or the metal film. And they have a little ceramic tube which is coated with either the metallized coating or a carbon coating up to a specific thickness. And the thicker the carbon coating on it and the type of the composition they're putting on it, the more conductive it will be. But then they can fine-tune that. They actually cut a spiral around it, and that creates a long, thin path of the carbon, and that increases the value of the resistance. And once they've done that, they put a metal cap on the end with the leads coming off, and they dip it in a sort of, I suppose it's a lacquer really. And typically with the carbon film resistors, which are my favourite, they're one of the easiest to read, it'll be this sort of beigey coloured, I'm not sure, what would you call that colour? I've never really thought about that. Beige, let's call it beige, it's sort of rich beige. And the metal film resistors, which I don't like, because they're usually blue, and they're really hard to read. The blue colour makes the colour bands, makes it easy to mix like colours like orange and brown, because they've got such a dark background. But I'll go into those colours afterwards. So that's the function of a resistor. I'm not going to go into it too much at the moment, because at the end of the video I'll cover things like Ohm's law, but I don't want to bore the pants off you, so let's move on to capacitors. Oh, I should continue and say about the resistors. The function of a resistor is to limit the current flow. So say for instance you had an LED, you wanted an LED to light from a battery. If you connected the LED straight across the battery, it would burn the LED out in most instances. But if you put a resistor in series with let's just draw it as a physical LED, and you hook it across the plus 12 volts, and 0 volts, then by choosing the resistor value you can actually limit the current to the correct value for the LED. They're also used for things like time delays. You might have a resistor charging up a capacitor, it trickles the current into it until the voltage reaches a certain level, and then that could be used as a timing function. And you also get variable resistors where effectively it's a carbon track connected at both ends. You only really need to use it connect at one end, and with a wiper that actually wipes round that track, so that depending on its position, that will vary the resistance. So let's move on to capacitors now, because they're quite interesting. So a capacitor, in its most basic form, is a layer of insulating material with a conductive surface on each side. And the best way to describe a capacitor in the water flow theory is a chamber with a diaphragm in it that stops the water flowing directly through. And that diaphragm can flex a certain amount in either direction. So if, say for instance, you connect it across a battery, the positive charge would flow in at this side, and it would cause it to flex over to the negative side. It doesn't actually physically work like this, but this is a good way to describe it. And if you reverse the polarity then, that charge, that amount that had filled up, would then be pushed out the other side, and it would flex the other way. And this allows, capacitors can be used to basically hold a charge of electricity, or in the case of the AC capacitors, that you often see me using these in my LED lamps, that diaphragm, it means that on the AC, on each half wave when the polarity swaps, that will let through a small amount of energy. The sort of electrons will flow backwards and forwards through it, but not just pass right through like a sort of short circuit. So to describe the capacitor, to actually show you what a capacitor does, let's make one. So I've got a bit of a cardboard here. This is a standard 6x4 photo piece of photo material. And I've got 2 bits of metallized film. So let's stick the metallized film on either side. So we've got a metal electrode, and I'm sticking it onto the insulator, the dielectric. And this is old aluminium tape, I think, because it doesn't seem to stick very well. But that's alright, it'll do what we need to do. And then the other side of this, I'll stick the other bit of tape, and that's the other electrode. And this is the physical construction that's used throughout all capacitors. They're all pretty much like this, but not using cardboard and aluminium foil. So let's get that pretty much as close to the other one alignment as possible. And the 2 factors determining the capacitance here are the area of metallization that's in parallel with the other one, and how thick the insulator is in between. And you'd think, you know, this card, it's very thin, so it's going to be quite it's going to be a modestly high value of capacitance, but that's not true. This is not going to be a high value of capacitance at all. So let's put this round, let's be optimistic and say 200 nanofarad. And I'll connect it one side and the other side. And the capacitance is actually, I'm actually connecting onto the adhesive side here. My capacitor measures oh, that's terrible, isn't it? It's 1.8 nanofarad. It's not very high at all. And if I was to cut this in half, so the actual, to prove that the area of the foil affects the capacitance, if I get a pair of scissors, and I cut this in half right now, so it's 1.83. If I cut that in half, it's half the capacitance. It's now 0.8. And if I cut that again in half, it'll go down to about 0.4, which it has. So that's basically how a capacitor works. It's basically an insulator, the 2 metal plates on either side, and the area of the metallization and the thinness of the separator is what determines the capacitance. And to get the value of capacitance up, that means that in reality, for components like this little 100, keep in mind that I managed, what was that, just a couple of nanofarad? This one is rated 100 nanofarad. And if you look at things like this, this is an electrolytic capacitor which is rated 470 microfarad, which is a massive capacitance. And to achieve that, let's get the notepad back in again. To achieve the higher capacitance, they often make the capacitors multi-layer. So this is something I just printed out, designed it on the computer for the printed circuit board design sort of layout, but I just did it as a sort of graphic. And if you can imagine that the blue is layers of insulation in the ceramic capacitors, and these are metallized sort of plates, then by alternating the pole, sort of creating a sort of comb of them with insulators, and then putting a metallization down the end to connect them all together, you can create quite a large capacitance in a small area just by making it a multi-story capacitor, so to speak. And that's still the layers of insulation in these, it's still going to be super thin. You'd need a microscope probably to see all the layers. Where you're going for a high voltage capacitor, the size has to go up. These are also 100 nanofarad. So you look at this one, it's 100 nanofarad, it's really small, but it's a low voltage one. when you're increasing the voltage, you have to increase the thickness of the dielectric, the insulation between them. And to make this type of capacitor, these are metallized film capacitors, and it's a film that's metallized on one side. And they take two strips of it, and they basically sandwich them together. And the plastic aspect of it is the insulator, and the metallization is the electrode. And to fit a lot in a small area, they then actually just spiral. They take a big long strip and they spiral it round into a small area, and that's what creates the sort of larger area. And the thickness of the plastic film itself will determine the voltage rating. This is a ceramic disc capacitor, usually quite low values. It's usually one of the simplest, and it usually is just a disc of ceramic with a conductive layer on both sides, and then an electrode that just comes across and comes off, and then it's dipped in insulation. But when you think that even this one is rated 10 nanofarad, and it's rated 1000 volts, but to get that 10 nanofarad, the insulation must be really, really thin inside that. I've never actually opened one of these up. Let's open one of them up right now and take a look. Oh, not this thing to do with your snips. Oh, that is so... it really is wafer thin in there. It's so thin that most of the thickness of that is the protective coating. That is super thin in there. I don't know if you can even see that. It just looks like a line. So, electrolytic capacitors are one of the more exciting capacitors, and I don't mean that in a good way. The electrolytic capacitors, to achieve such a high capacitance, they contain a liquid electrolyte. And they have a very thin foil inside. And the foil, to create an extremely thin insulator, they form an oxide layer on the aluminium foil in there. And that means it really is like micron thick, which means that they can get a very high capacitance in a small area. But to couple onto that surface, they have to use a liquid electrolyte, which then, because if you looked at the foil, it would look all pitted and mottled with that oxide coating. So to get a good coupling, they use a liquid that just fills in those gaps. And that's one of the downsides of, well, it's many of the downsides of the electrolytic capacitor. Because traditionally, all the old, say for instance, all the old video games from the 80s tend to suffer problems after a while with what's called drying out of the electrolytics. They still measure the correct the capacitance, but their equivalent sort of resistance, the resistance to current flow through them changes, it increases. And what that means is that they stop doing their job properly. In when you get the large values like this, they're usually used to smooth ripples. So say for instance you had the output from the mains was rectified, and you had a big peaky sort of like the AC full wave rectified AC waveform, which is like the two sides of a sine wave. Then by putting this across that, it then just it reduces it to a very slight ripple and a nice smooth DC voltage. And as that capacitor dries out over time, that ripple will get bigger, and it ultimately starts causing problems when it dips down so low that the electronics can't sustain normal operation. And that's when you have to change capacitors. However, that's more of an issue with modern electronics, because whereas in the old days, these capacitors only had to deal with like 100 Hertz or 120 Hertz, just mains frequency rectified. Nowadays, the capacitors have to deal with the output from switch mode power supplies, which is like thousands of hertz, tens of thousands of hertz, and it means that they actually heat up and they dissipate more energy. They're put under a lot more stress. And if you look at the top of this one, you'll see there's a little cross on it, and that's a safety vent, because when these fail, what actually happens is that oxide coating can be perforated, and that's really common if you accidentally connect them in reverse, because it relies on the polarity to keep that oxide coating intact. When you connect them in reverse, that fails, and then suddenly you've basically got this liquid-filled thing just connected across the power supply with no current limiting it. Just basically it turns into sort of resistor, and it boils the electrolyte. And when that happens, the top will either sort of, if you looked at from the side, it would bulge up. But if it goes too far, that X that's etched onto the top will split open, and it will vent out the top. And the other option there, if it doesn't do that, is sometimes it blows the whole can off, and it just makes a mess. It gives out a vapour of the electrolyte, which is slightly caustic. It can unravel the foil across the room. It can go off with enough force to actually cause injury if it hits you. So you have to be kind of careful with electrolytic capacitors. So what do we cover? Let's look at diodes now. Diodes come in various flavours. They're used for various functions. You get signal diodes, rectifier diodes, and light-emitting diodes. The function of a diode is to allow current to flow in one direction, but not the other. So the symbol for a diode, I didn't mention the symbol for a capacitor was that, basically representing the two metal plates with a sort of air gap in between. And the case of the electrolytic, that has the positive and negative are marked with the positive being the sort of just the empty box and the negative being the sort of filled box, just for the polarity reference. However, moving on to the diodes, the symbol for a diode is very easy. It's very self-explanatory. In the water equivalence thing, it would be a pipe with a one-way valve in it, so the water could only flow one way. In this case, you have the anode of the diode and the cathode, spelt with a K. I'm not sure why they do that. There must be some reason. I've never really investigated that too much. But current will flow positive from the anode. It will flow through the diode to the negative. But if you try reversing the polarity, very little current, if any, will flow through that diode in reverse. And the main values you have to consider with diodes are the current you want to flow through them. Say, for instance, this is a 1 amp diode. It's rated to handle 1 amp flowing through it. Something like a 1N4148 signal diode. It's not designed for anything major. It's just designed for, say, rectifying small electrical signals. So it's only rated about 100 milliamps or so, if that. And the other factor is the peak inverse voltage. That's what sort of voltage it will block coming in the wrong direction. So supposing if you did connect, well, this one is a 1N4007, it's rated 1000 volts. So that means that it will block 1000 volts going the wrong direction. But if you were to exceed that dramatically, it will avalanche and it will start conducting the opposite direction. So you have to choose the correct diode for the job. This is a silicon diode, which typically has when it's forward passing current in the correct direction, positive to negative, it will typically have a voltage drop of about 0.6 volts. Sometimes, it depends on the voltage rating. It'll actually sometimes go up to 1 volt, and it also depends on the current flowing through it. You get Schottky diodes, which have a much lower forward voltage of between 0.2 to 0.5 volts, and in cases of rectification, that lower voltage actually makes them much more efficient. The light emitting diode, our favourite type of diode really, is a diode junction that is optimized. It behaves in a way like a normal diode, but when it's forward biased, when the current's flowing through it, it emits light. And the very first LEDs were actually, here's some here, they look just like the 1N4148. These are actually LEDs. They look just like ordinary glass diodes, but these are really vintage LEDs. And when you actually pass current through them, in the correct direction, a little red dot glows inside them. It's very, very dim, but they were purely for printed circuit board indicators. These days, of course, LEDs are used for illumination. They've evolved greatly. But one of the things you have to note with an LED is they don't have a very high, because they're optimized for emitting light, they don't have a high reverse blocking voltage. It's usually just about 5 volts. So if you were to connect the polarity wrong in this and exceed about 5 volts, then in the case of white, blue, green LEDs, it may damage them, but with red ones, they may end up just conducting but not lighting in the wrong direction, but not suffer damage. So let's the other diodes, Zener diodes. A Zener diode is a diode used for voltage regulation or provide a voltage reference. It will act like a normal diode if you pass current through it in the normal direction, and it drops roughly about 0.6 volts. But you get them, say for instance you want a 5 volt supply, you get a 5 volt Zener, and when you actually apply a reverse current, positive flowing down to negative, it will actually start conducting fairly precisely at 5 volts. So if you limit the current through the resistor that limits the current flow, then the voltage will just sit round about 5 volts, and that's often used to provide very simple power supplies and regulation in the circuitry. Let me think what's next. I think we may actually be going in the direction of the resistors again, and let's look at transistors. The world of transistors is huge. There are so many different types of transistors. You get the small transistors, you get the big transistors. One of the most common ones I tend to use for small projects is just a little BC547. An equivalent in America might roughly be 2N3904. And for simplicity, I'm just going to show the basic NPN silicon transistor, one of the oldest fashioned type transistors about. And the symbol for it is this. You get 3 pins, and if you ever want to find out what the pinout for your transistor is, if you're not 100% sure, just go on Google and type its number in, like 2N3904. Google it, look for images, and you'll find pictures of the transistor with the actual pin designations actually just printed under them. It just makes it very easy to find data like that. So it's got 3 pins. It's got the base pin, it's got the collector pin, and the emitter pin. In the case of an NPN transistor, it's usually switching something down to the ground rail, the negative rail, or the 0 volt rail. And it's used as an amplifier or switch. Supposing, for instance, you had a small tungsten lamp, and you had, say, a 5 volt supply. If you wanted to control that lamp, if you wanted to turn the lamp on and off, but you only had very limited current available, you can use a transistor, and as soon as you exceed about 0.6 volts, because it's silicon again, that's the standard sort of silicon junction voltage, above the ground rail here, the 0 volts, and a modest current, a transistor typically has a value called a gain. It's got a voltage rating, a gain rating, a power dissipation rating. There are lots of other ratings, but really, let's keep it simple and say, because in most instances when you're using a transistor, it's going to be an NPN that's going to be like this. So, say for instance, you've got a gain of 100, and that lamp's going to pass 100 milliamps to light fully. Then you want to pass at least 1 milliamp into the base here, and that will then be multiplied by the gain of the transistor, and it will switch the lamp. So it's like a relay, but it's no moving parts, and it's a little electronic switch. It's just a really handy little thing. You can also use them in other formats, like for voltage current regulation, things like that. But just knowing the basic operation that, as soon as the base has X amount of current going in at roughly about 0.6 volts above the emitter here, then the collector current will flow. That's all you really need to know. It's just to get started. Other types of transistors are things like this one pictured here is a MOSFET, and they're optimized for switching really high loads, and that one is, I chose the STP36NF06L for my RGB controllers because one of the nicest things about it, it can handle a lot of current, and its on-state resistance is so low it doesn't impede the flow of current when it's turned on to such a level that it doesn't really get very warm. You can use it to switch quite a modest current without having to worry even about applying a heatsink to it. Because traditional transistors would have a slight voltage drop across them, and that would result in heat dissipating. So MOSFETs are much better for that. They also have an extremely sensitive input, but they generally require a much higher voltage on their gate, as they call it, to actually turn on. But the current flow is virtually zero that's required to turn these on. It's a sort of capacitive effect. They're quite amazing things. You also get a hybrid. The MOSFETs are not as robust as the traditional let's see, bipolar transistor like this one. So you get a hybrid called an IGBT, an insulated gate bipolar transistor, which is almost like a traditional transistor with sort of low gain, but with one of these transistors on the front of it. So it's very easy to turn it on. It can switch massive currents, and it's really a robust transistor. But you can find all that online if you actually look for it. This is just a basic guide. So let's now look into things like Ohm's law. Ohm's law, which is just a couple of formulas, really easy. And the best way to remember them is with a triangle. V equals I times R, where I, let's draw that out a wee bit wider, and actually what they actually are, voltage equals current, which is I, times resistance, which is ohms. He said, drawing right out his triangle. Okay, that's all right. And an application of this would be, supposing you had a 12 volt supply and you had 3 LEDs. So there's the 3 LEDs, and each one is dropping about 2 volts each. And you want to choose a resistor that is going to limit the current, so that's at 0 volts over there. You want to choose a resistor that's going to limit the current through these LEDs to 10 milliamps. So across the LEDs, you've got 6 volts dropped. Across the resistor, because it's a 12 volt supply, you've got the 6 across the LEDs, and you're going to have 6 volts across the resistor to drop. So to work out the choice of the resistor value in ohms, you would R equals V over I. Oh, sorry, I should mention here, V equals IR, but if the reason I've drawn it a triangle, voltage equals current times resistance, but if you want to reverse that formula, resistance equals voltage divided by current, and current equals voltage divided by resistance. That's why I've drawn it in the triangle here. So voltage equals current times resistance, and for the other ones, you divide the one above it, much as you'd write it if you're actually doing the sort of mathematical formula. R equals V over I and I equals V over R. It's just an easy way to remember how they relate to each other. So to calculate resistor, resistor equals voltage to be dropped over the current. So it's 6 volts to be dropped, 6 volts divided by the current you want, which is 0.01 amp, which is 10 milliamps. So if you bring the calculator in for that, I don't need to use the calculator, but I will use the calculator for this. 6 volts divided by 0.01, 10 milliamps, equals 600 ohms. 600 ohms. Now, that's not a standard value, the 600 ohms. You would have to use the nearest standard value, which might be 560 ohms or 680 ohms. And the other way this formula can be used is to, if you are trying to measure how much current's flowing through some existing LEDs, say for instance you're measuring some LED tape, and you might find that actually putting an ammeter in series with it, because the voltage drop across the resistor in series with the LEDs is so low, putting an ammeter in actually skews the reading a bit. So say for instance you've got a 12 volt supply and it's feeding more LEDs, but you don't know the voltage across the LEDs, and you don't know the current through them, but there's a resistor and you do know the value of the resistor. So if that's, say for instance, a 330 ohm resistor, 330 ohm resistor, and you measure the voltage across that while the LEDs are running, and you measure 5 volts. And to calculate how much current's flowing through that whole circuit, you would use the formula I equals V over R. So that's the voltage dropped across the resistor divided by the value of the resistor, which is 330 ohms, equals, so that's 5 volts divided by the 330 ohm resistor value equals 0.015. So the answer is, it's drawing about 15 milliamps. The 15 milliamps is passing through that circuit. So it's useful to be able to do it that way. Now, resistors, there are a couple of variables with them. You can choose the resistance value, say for instance this is a 1 kilo ohm, And you can also choose the power rating, because if you use too small a resistor, it can actually go up in smoke. Would you like me to demonstrate that? I think you would like me to demonstrate that. Let's use this handily placed 10 ohm resistor I've got here, which is just trying to escape at the moment because it knows what's about to happen to it. So this is a 10 ohm resistor. Its colour code is brown, black, black, 1, 0 and no zeros at the end. So I'm going to connect it across 12 volts. And when I do that, it's going to grossly exceed its power rating. A current of about 1 amp is going to flow through it, which means it's going to dissipate about 12 watts, which is only rated quarter watts. So it's going to be the best part of 50 times its rating. So let's see what happens. It's smoking, glowing, and it just burst into flames and failed. Okay, would you like to see that again? Yes, you would. So let's get another 10 ohm resistor here. Hook it up and we'll see it burst into flames again. Oop. Lots of smoke and my workshop is now absolutely stinking. So yeah, so you have to choose the correct power rating for resistors. How do you work that out? That's where another formula comes in. Very simple. Triangle again. P, power, equals current times voltage. So say for instance, let's choose an example of this interesting 10 watt red LED, which is a voltage when it's operating about 9 volts and requires about an amp, which, you know, to give it the power rating of the LED itself, that's the 9 volts times 1 amp is 9 watts. So to calculate, if we were to actually put a resistor at 12 volt supply again, and choose a resistor to limit the current through this to the 1 amp. So let's see, here's the, I'll just draw it as a huge big LED. I'm not going to draw what's in it. There's a 3 by 3 array. But the voltage across that is about 9 volts. So we've got 3 volts to drop across the resistor. And if we go back to the original formula, R equals V over I, we've got 3 volts divided by the 1 amp we need, so that's going to be about 3 ohms. But to actually work out the power rating of it, we have to multiply power equals the current through the resistor times the voltage across it. So this has got 3 volts across it, it's 1 amp, it's going to dissipate 3 watts. But we'd actually be better choosing a higher power resistor. And it's not a terribly efficient way to drive the LEDs, but it works. It's very, very simple. I'd probably choose a 5 watt resistor because you want it to stay cool. You often see resistors that have just been pushed too far on printed circuit boards. You know, they've been designed and they've said, I need a 1 watt resistor. They use a 1 watt resistor, and instead of a nice colour code, it's basically the whole thing is just brown, and the circuit board shows heat round it as well. So it's good to dissipate, get rid of that heat. The colour codes. This is the colour code for resistors. Now, a resistor has markings on it. In the case of this one here, this 1000 ohm resistor, it's got one band here, which is brown. It's got a black band. Actually, let's write it like that. Black. And it's got another band which is red. And then at the end, it's got a band which is gold. The gold band at the end indicates the tolerance. What's really important for us is the first 3 bands in this. The one at the end, the gold one, indicates the tolerance. In this case, it's 5% tolerance, and it just means that it's going to be within 5% of the. If you measure the resistance of this, it's 1000 ohms. It's going to be, you know, within 5% of 1000 ohms. The colour code itself is worked out like this. The first line is the first number. The first band is the first number. So in the case of brown, it means 1. So that's 1. The black means 0. And the red means 2. But the third code is actually a multiplier. So in the case of the red one, it means there's 2 zeros. 2 zeros equals 1000 ohms. If you had a 47 ohm resistor, it would be yellow for the 4, violet for the 7, and then because there are no zeros after that, it would be black band. Yellow, violet, black would be 47 ohms. If it's going to be a much lower value, like 4.7 ohms, you'll get basically a divider, either gold or silver, where the first two digits, if it's followed by a gold band, it will be first digit, point, second digit. So for instance, 4.7 would be yellow, violet, gold, and it would be 4.7. Or for even lower values, I can't say I've ever really come across silver often. It's 0 point and then the first two bands. So that would be, in the case of the 4 and 7, the yellow and violet, it would be 0.47 ohms, very small value. So there are ways to remember this. The one I was taught with is Billy Brown revives on your gin but values good whiskey. And that's basically the colours in sequence, the first letter of the colours, starting at 0 and going up to 9. And this is one of these things that it seems a bit daunting when you have to remember a colour code like this, but the more you do it, the easier it gets. And there are really rude ones. I mean, it's helpful when the first word is actually the colour, because the first two letters are B, unfortunately. So Billy Brown, the brown indicated the brown colour. But you also get the really rude one, black boys ride our young girls, but virgins go without, which is, strangely, the rude ones are the easiest ones to remember. I mean, I would try and be politically correct and say, you must only use really polite ones. But to be honest, the ruder ones, I mean, by all means, you guys, if you're familiar with the colour code and you have one that you like to remember things by, no matter how rude it is, within reason, put it in the comments down below. But the ruder ones are just the easiest to remember. And once you've, after you've been using resistors and doing, reading the colour codes for a while, you'll just look at a resistor and go, 1K. Just look at it and just instantly know the value. It's how it is. The same colour code is sometimes used on older capacitors, and it's still used on inductors, which look very much like resistors. That's just a summary. I mean, I'm not going to go into in too much detail because it would get boring very, very quickly. But this is just the basics of what you need to know, how to work out the power rating of a resistor if you're driving quite a heavy load with it. In most instances, a standard quarter-watt resistor is fine, and how to choose the resistance value to limit current to whatever you want through LEDs and things like that. So fundamentally, that's it. Hopefully that's sort of helped, and I've not overcomplicated it as I sometimes do. And that's put some of the jigsaw pieces together, because as you understand it and as you build stuff with electronics, and to be honest, the best way to learn electronics is buy kits, build them, blow them up, have a little incidents, try and fix them, maybe fix them successfully, and that way everything will just fall into place, and you'll just suddenly realise that, without even noticing it, that you suddenly know how all these components work and what they do and how to select them. It's just a natural thing that evolves over time.